Hey there, everybody. Welcome back. Today, we're bringing you surface integrals. This is Chat 15.5 in Anton's 11th edition book for calculus. This is Calculus 3 at College of the Sequoias. Fall of 2022. Let's just jump right into it. 15.5, we're doing a lot of physics-based stuff. This is a segue. This section is a segue to stuff we're going to do with later stuff with divergence theorem and stuff like that. So surface integrals, we've looked at special surfaces before, you know, spheres, cylinders, we've got paraboloids, hyperboloids, stuff like that. What about like a general surface is just not a plane, but a general surface that could be wavy, it just could be crazy shape. We can describe the surface by a vector, of course. It's any given point. We're going to use R of UV is X, the X component, Y component, Z component, where each component, X, Y, and Z, can be a function of two parameters. We're going to use U and V. There are two useful families of curves that lie on that surface where it's parameterized U and V. The curves where U is held constant and where V is held constant. So where U is held constant, that's actually kind of where we have our partial derivatives of R with respect to V. And where V is held constant, going that way is kind of like where we have our partial derivatives of R with respect to U. When we look at a point, P, we can do more with it. Those are called grid curves, mind you. They're not necessarily straight. So at a point P, we can make a tangent plane. The tangent plane has a normal, n equals ABC. And with that normal, we can make the equation for the plane, a times x minus x1 plus b times y minus y1 plus c times z minus z1. We've done all this before. N was the cross product of the derivative of r with respect to u and r with respect to v. This is old news. If n doesn't equal 0, the surface is smooth. It's got no corners. That's actually how we motivated the Jacobian. Back in chapter 14. The Jacobian was the absolute value of RU cross RV. After we took the magnitude. Yeah. So I should add a little bit more lines in there. We had the magnitude and cross part. And it's what we use to change variables for planar surfaces. Now we want to look at something different. We aren't using a dA as a planar surface. We're going to use ds for a general surface. And that's a big S. We had a little s for line integrals. I don't know why we used S for, well, I know why we used S for line integrals, arc length. We're going to use S for surface here, unfortunately. I'm deliberately making the S as big as a C, but dA over ds, the process hasn't really changed from when we did the Jacobian setup. So we aren't just finding area, we are effectively taking that curvy surface in S, and we're going to map it to a planar region D where it's easier to integrate. Because it's nice and flat, it's easier to integrate. And that's what we're doing when we take f of x, y, z, and we're doing our surface integral. We're going to map it over to RU and U and V where it's planar. Okay? This changes the variables. It's a change of variables, basically, from S to V. Surface S to planar D. And it should look fairly familiar. This looks a hell of a lot like line integral, right? Surface is f of RUV. Line integral was f of xt and yt. So single variable for line, double variable for r. In both cases, we have a correction factor that is the magnitude of some vector. Looks very similar. Let's do some examples in the next video. Peace.